Dear students, happy Dashaya. I hope you are all safe in the pandemic, and I've decided to change my mode of giving the slides for the course because I think it's absolutely boring to have a slide that you see in the screen and somebody is speaking from the back. It's always better to see the faculty member and also see his reactions for what is he doing, maybe sipping a cup of tea just like this. Kanpur, many of whom you are not in this city, it becomes slightly cold outside. So when I am talking to you through this mode, I am essentially in a class mode, so I'm inside my study at my home. So what I can do is that we can talk in a much more relaxed way. Today we are going to talk about examples of convex sets. You know what a convex set is, that if you have a set and you take 2 points, any 2 points on it, join them by a line segment, the line segment should lie in the set. But the question of course lies, what are the examples? The simplest examples are the set, singleton set, which consists of the origin of Rn and the whole set Rn itself, right? But one of the useful class of convex sets is the notion of hyperplanes and half spaces, which we will use in a very important way when we talk about separation theorem. And separation theorem are the keys on which whole of optimization ideas actually is there and actually is holding on. So first we talk about this plane, hyperplane is called HAB, which means that it consists of all x in Rn, which satisfies the following equation. Inner product of the vector A with x is equal to the real number B. Now A is given in Rn, B is given in R. These are fixed numbers, fixed vector and fixed number. Now what is the meaning? How do you geometrically view it? Let us look at it in 2 dimensions. When x is consisting of variables x1, x2, 2 coordinates, and A of course is a vector in R2 consisting of 2 vectors a1, a2, they are fixed of course. So the inner product is a1 x1 plus a2 x2, and that is must be equal to some b. So that b is given. So this a1 x1 plus a2 x2 equal to b is same as writing a inner product x equal to b. So which means in R2 hyperplane represents a straight line. In R3 it would represent a plane. In R4 you might call it a hyperplane, and that is why the name hyperplane is given. Now comes this interesting spaces. So if you draw a line on a piece of paper, you see the piece of paper is kind of boundary wall. It divides the whole R2, the plane of the paper, into 2 spaces. The one, suppose you draw a line like this, the one on the upper part is called the upper half space, one on the lower part is called the lower half space, and that is exactly the way we have defined the sets here, that the upper half space is set of all x in Rn such that the inner product of Ax is bigger than B, and the lower one is just reversing the inequality, and the boundary wall is exactly the hyperplane. These are very, very important where we want to actually separate convex sets in 2 different domains, and that's the idea of separation theorem, which would come at the very end of your study of convexity. Okay, so we would also talk about another important class of sets before we close this little topic, because I don't want to stretch too much. I will give in small classes because I'm taking the video on, it becomes quite heavy this. So another important class of sets is the polyhedral set. So what is a polyhedral set doing? Polyhedral set is a very nice looking set because it is the intersection of half spaces. So you half space means you draw a line and paint half part of that, and then take another line, draw, paint, and half part of that, and then see what are the, take 3-4 of them, whatever, 10, and then see what is the intersection zone. That set would be a convex set. And you can ask why it is a convex set, because the intersection of 2 convex sets would be convex, and that is why it is a convex set. So I have not yet tell you what are the properties of the convex set, but for the moment you take from me that this will form a convex set. So intersection of half spaces is called will be a convex set, and you can prove it. I do not need to prove that the intersection of half spaces, intersection of convex sets is convex. I don't need to prove it first. You can just prove that polyhedral sets are convex set just by using the definition of a half space. right? So I hope this polyhedral set plays a very important role in optimization. There's a large kind of type of application problem deals with the minimization of a convex function or maximization of a concave function, maybe quadratic, over a polyhedral set. Linear programming is completely dependent on the theory of polyhedral convex sets because its feasible sets are intrinsically polyhedral. So this is a kind of set that we will encounter pretty often, and so please keep this in mind. And at home you can try to use the definition that polyhedral set is a finite intersection of half spaces. So take 2-3 different half spaces and intersect them, and then try to see whether the intersection you can prove that is a convex set, that is taking 2 points, show that lambda x1 plus 1 minus lambda x2 will be in that intersection. So that's a little work. You should do it for yourself to convince yourself that the polyhedral set is actually a convex set. So thank you very much. We will come back very soon in the next lecture, which would be essentially about convex functions. Okay. Thank you for your attention.